Hey, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through some definitions you need to know for linear algebra. So linear algebra is concerning the studying of linear equations. So something like this, 2x plus y equals 9, that is a linear equation. It's an equation because it has an equal sign. It's linear because the two variables, in this case x and y, both have a power of 1. So we tend to represent linear equations as matrices, and linear algebra is dedicated to the study of those representations. It's the study of matrices. So what I'm going to do is I'm going to give you a lot of definitions that you will need to know for studying later lessons. So I'm going to go through each one and tell you why it is important. So the first definition we will go through is that of a matrix. So matrix is singular, the plural is matrices. So a matrix is just a rectangular array of numbers enclosed in a box. So I'm just going to populate this with numbers. Let's say 1, 2, 5, minus 1, 0, 9. Okay, so that is what a matrix looks like. And we usually name matrices with a capital letter to distinguish them from vectors, which you'll learn later. So that is an example of a matrix. Of course, they won't all have the same number of numbers inside. So you can see there are 6 numbers inside A. Each of those is called an element. So A has 6 elements. But I can make matrices of different sizes. So B, I might make, say, 1, 2, 3, 4. That is a matrix. C, I'll make another matrix. This one's going to be the same size as B. So it can have positive and negative real numbers. Now, to be a proper matrix, each row and column has to have the same number of elements. So I can't have a matrix that looks like this. Okay? That's not a proper matrix, because there are not the same number of elements in each row and column. So rows go across and columns go up or down. Okay, so rows left and right, columns up and down. So you can see in this non-matrix, this particular column has 2 elements, whereas this one only had 1. That's why it wasn't a proper matrix. So we need to first be able to write the order of each of these matrices. So the order is just the size, and we write it as the number of rows times the number of columns. We always write the number of rows first. So if we look at matrix A, it has 2 rows and 3 columns. So it is a 2 by 3 matrix. B has 2 rows and 2 columns, and similarly C has 2 rows and 2 columns. So why is this definition important? Well, the order of matrices completely determines whether or not you can add, subtract, or multiply them. If the orders don't match up properly, and you'll learn what that means later, then you can't actually add them, subtract them, or multiply them. So order or size of a matrix is the number of rows times the number of columns. Now, if a matrix has the same number of rows as it does columns, we call it a square matrix. So both B and C are examples of a square matrix. A is not, however. It has a different number of rows and columns. It has more columns than rows, okay? So this is a very important definition because there are some things we'll look at that only exist for square matrices. For example, when we look at matrix inverses or the trace of a matrix, we're only interested in square matrix. So we also have a special way of labeling the individual elements in a matrix. So we use a capital letter to represent the matrix as a whole, but when we're representing individual elements of that matrix, we use a small letter. So small letter A means an element from the matrix big A. So we give it 2 numbers, like 1, 2. So A1, 2 means the element in matrix A that is in row 1, column 2. We always write row first. So row 1 is this one, column 2 is this one, so we're talking about this element here. So A12 is equal to 2. If I wrote something like B11, that is the element in matrix B in row 1, column 1. So that's just 1. And say C21 would be the element in matrix C in row 2, column 1, which is 3. Okay, now when you're adding and subtracting matrices, note that it isn't always possible. The two matrices, in order to be added or subtracted, must be the exact same size. So if we look at the matrices above, if I wanted to add A and B, I actually couldn't do that because they are different sizes. I could, however, add B and C together because they are the exact same size. And in this case, I just add the corresponding elements. So I add the two 1, 1 elements together, B11 plus C11 to get 1. Similarly, 2 plus minus 1, so that's the 1, 2 element in each of those. Then I do 3 plus 3 and 4 plus 5. Okay, so adding and subtracting matrices is easy. That's how you add. And if I wanted to subtract, I'd do the same thing, except instead of adding, I would subtract the corresponding elements. So I'd subtract the 1, 1 elements, 1 minus 0, 2 minus minus 1, 3 minus 3 for the 2, 1 element, and then the 2, 2 element is 4 minus 5, okay? How easy is that? So note, when I add or subtract matrices, the resulting matrix is the same size as the two matrices in the sum or the difference. Now, multiplying matrices is actually more complicated, and we're going to look at that in a later lesson. But for now, that's how you add and subtract matrices. So going back to our definitions, another important definition to know is the trace of a matrix. So we call it TR for trace. So we're only interested in the trace of a square matrix. So we're not really interested in the trace of A. So the trace of a matrix B, what you do is you add all the elements on the leading diagonal. So the leading diagonal, you start at the 1, 1 element and you just go down in a diagonal line like that. So what we're actually after is the 1, 1 element added to the 2, 2 element, to the 3, 3 element, and so on. Of course, in this matrix here, we don't have a 3, 3 element because it only has 2 rows and 2 columns. So it's just all the numbers added together on the leading diagonal. So the trace of B in this case would just be 1 plus 4, which is 5. So the trace is actually very important. Things like eigenvalues. It turns out the trace of a matrix is the same as the sum of all the eigenvalues, but we'll learn what an eigenvalue is later. Another important thing about the trace is when we look at similar matrices, which we will do later, they actually have the same trace. So if two matrices are similar, then they have the same trace. But for now, you just need to know the trace is the sum of the elements on the leading diagonal, and the leading diagonal includes the 1, 1 element, the 2, 2 element, 3, 3 element, 4, 4 element, and so on. So now we're going to look at some special types of matrices. So we now look at some special types of matrices. So the first one we're going to look at is upper triangular. So that is a matrix in which each element below the leading diagonal is 0. So it can be any size matrix. So let's create one. So I have one like 1, 2, 3, 4. So then if I make this a 4 by 4 matrix, this element would have to be 0. So I might have something like this. Then these two would have to be 0. And these 3. Okay, so this would be an example of an upper triangular matrix. You can see sort of like a triangle here. So this is the leading diagonal here. All entries below it are 0. That's what makes this matrix upper triangular. Okay, so lower triangular is just the opposite. This one I'll make a 3 by 3 matrix. So I'll have my leading diagonal here. So all entries that are above the leading diagonal will be 0. So all of these would have to be 0, and these can be whatever they want. So if a matrix is both upper triangular and lower triangular, it is diagonal. In order to satisfy both these definitions, it would have to have zeros above the leading diagonal and also below the leading diagonal. So it doesn't necessarily need to be a square matrix. So I'm going to make this one a rectangular matrix. Let's make it a 3x4 matrix. So something like this is a diagonal matrix. Every element that is not on the leading diagonal is 0. So the leading diagonal is here. So it's upper triangular because all of the entries below the leading diagonal are 0, and it's lower triangular because all the entries above the leading diagonal are 0. Okay, so a diagonal matrix has all elements off the leading diagonal equal to 0. So these are very important definitions. To give you an example of where they're useful, what computers do to solve systems of linear equations, they will actually try and write matrices as the product of an upper triangular and a lower triangular matrix. It's called an LU decomposition. And that actually makes solving systems of simultaneous equations so much easier, and in computer terms it makes it much more efficient because you need far fewer operations. Now, it's not always possible to write a matrix as a lower triangular matrix times an upper triangular matrix, but when it is possible, it makes the computation so much more efficient. These matrices are so much easier to work with when calculating things like eigenvalues or whatever. So that's why triangular matrices are important, and the diagonal matrix is an example of triangular matrix. So the identity matrix is something we'll look at a lot more later. So it's called identity matrix because it preserves identity under multiplication. If you multiply a matrix by the identity matrix, it doesn't change it. So it needs to be a square matrix and it needs to be diagonal, but all the entries on the diagonal are 1. So there's a different identity for each number, each whole number. So I1, we don't really look at 1x1 matrices, but I2 is a 2x2 matrix. 1's on the leading diagonal and 0's elsewhere. I3, for example, it's a 3x3 square matrix with 1's on the leading diagonal and 0's elsewhere. So we haven't looked at matrix multiplication yet, and we will eventually, but it turns out if you multiply a matrix by this or this, and the product is actually possible, then you won't change the original matrix. Okay, the last thing I need to go through is the transpose of a matrix. So let's say I have a matrix like this. So I'll make A 1, 2, 3, 4, 5, 6. So A is a 2x3 matrix. So the transpose of a matrix, which we denote AT, transpose just means switching. So here we switch the rows and the columns. So you can see that in A, 1, 2, 3 was the first row. So in A transpose, 1, 2, 3 will be the first column. And similarly, 4, 5, 6 was the second row in A, it'll be the second column in A transpose. So the rule here is that an element in A is the same as the element in A transpose if you just switch around the rows and the columns. So for example, 2 here, that was element A1, 2. So in A transpose, it becomes element A2, 1. Both of them are equal to 2. Okay, so transposes are very important. For example, we're going to look at matrices where the transpose of a matrix is its own inverse. It turns out that those type of matrices have special properties such as preserving the length of vectors. So that might not mean a lot to you at the moment, and that's fine. I just want you to know that they are very important. So a matrix in which A equals A transpose, that is called a symmetric matrix, okay? So of course a symmetric matrix would have to be square matrix because it would have to have the same number of rows and columns. So an example of a symmetric matrix is the identity, because if I have, say, the identity, the 2 by 2 identity, its transpose, if I just switch around the rows and the columns, the 1 stays where it is, this 0 gets moved here, this 0 up here, and you see I have the exact same matrix as I started with. So the identity is an example of a symmetric matrix in which the matrix is equal to its own transpose. All right, sorry there has been so many definitions, but these are very important for your study of linear algebra. This has been the luckiest maths teacher in the world. Have a great day.